Hello, everyone, in person and on the recording. So today we have Ankur Mali from the University of South Florida, who's going to be talking about provable stability of neural network Turing machines with bounded precision and time. And I guess I first came across Ankur's work on stack recurrent neural networks a couple of years ago, and also one of his papers was looking at stability of differentiable stack networks. And I think this work is going to be extending it to Turing machines or neural Turing machines, which I'm excited to hear more about. So yeah, Ankur, take it away.
Thanks, Will, for introducing me and inviting me to give this talk. So as Will pointed out, in this work, what we are trying to do, we design a new neural network architecture that is Turing complete with finite precision and also finite time. And also we show the solution of the model we have designed is stable. In other words, within a fixed point, model will always, throughout it will converge and will stay ideal to the true Turing machine. So other authors of this work are John Stogan. So he did his PhD from Princeton and he owns his own firm, and Lee Giles is David is a professor at Penn State. So before diving into this, so in this talk, I'll be motivating the audience that why we need universal Turing machine and how my current work aligns in context of all the related work concerning the Turing machine. So let's start with the simple motivation that why we need this. The assumption, since with the emergence of large language model, it is belief in machine learning community that they can solve anything, they can do reasoning, but rather they they simply learn the statistical pattern. And in no way they can be assumed Turing complete in finite precision and time. So Gary Marcus do talk about why we need a symbolic machine and why we need a universal machine, which can work in polynomial time as well. So symbolic machine, as we know, they are rule-based system. With minimal information, you can easily access the information from these machines. They're highly explainable. There's a faster communication. So if else complexity theory networks using XOR and can be derived from symbolic machines, same as state machines. Subsymbolic machines such as neural networks, where we learn from large amount of data. They are considered as least explainable, but they can adapt to a wide variety of domains. So what we want is we want machines to represent, incorporate, process, adapt, and retrieve symbols efficiently with minimal resources. So enter step towards reaching AGI. So representation, neosymbolic AI, and showing equivalence with Turing machine is an efficient way to move forward to show that what capability we have in terms of complexity of these networks. So Chomsky provided a nice containment hierarchy of class of formal languages. I won't be going over this in detail because there are several experts in this group. But in the simplest form, you can see the simplest language is regular language. And the machine which is designed to recognize such language is known as finite state automata. So it can be deterministic, it can be not deterministic. So when we add memory to these networks, you can get better capabilities and learn complex grammars. So a finite automata augmented with memory such as stack would give you context-free grammar or equivalence to pushdown automata. If you augment that with tape, you get the capability of Turing machines. So if a function can compute the recursive linear language, those are considered as Turing machines. So before diving into the models, which I'll be discussing in this talk, I would like to go over a few notations because I'll be talking about first order, second order, third order models. So before this, I just need to show what these notation means. So in the simplest form, a vector with d1 dimension is considered as 0th order. Matrix with 2 dimension is considered as first order, and existing neural networks fall into these categories since the weight of these networks are 2D in nature. So if you imagine LSTM, GRU, RNN transformers, all the weight matrices are 2D in nature, so that they can be categorized as first order networks. Next, we have tensor models. So if you consider stack of matrices, that will give you second order weight, which is in a form of cuboid, which is a stack of 2D matrix. Then there is third order network with 4 dimension, which is stack of second order tensors.
So in the second order network, in your version, what are the semantics of the different dimensions?
So in second order network, so you can insert the entire transition table into the weights of a neural network. So you can represent current input, current state, and next state. So this transition table can figure out what would be the next state of a network. So if you consider DFA, right? So the state transition or the transition table of DFA can be inserted into these networks. So that's where the semantic would go. One dimension would correspond to input, one dimension would correspond to the alphabet with respect to this and current state, and then how it is getting transferred to the next state or next state of automata. Does it make sense?
Yeah, thanks.
Okay. So this is how first order RNN can be represented, where model has inputted in weight matrix to insert symbols at each time step, then hidden to hidden weight matrix to store prior history, and hidden to output weight matrix to produce prediction at each time step. So you can imagine this as a state machine, where Kohavi did point at sequential network with information to prior history can be considered a state machine. So when I talk about first order, as you can see, the weight, the hidden to hidden weight matrix can be represented using 2 dimension, D1 and D2, which are indexed using INJ. And common framework or the common learning approach we use to update weight of these networks are using backpropagation or backpropagation through time. So this is going backward in time. And the minimal requirement for this is all weights or all activations should be differentiable. This is the minimal requirement we have for backprop to work stably. So prior work in finite precision and time, let's look at some prior work. So regular languages, RNNs and GRU are equivalent to regular languages. So Will and Gale in the 19 work, they did show that using saturated function analysis, the RNN GRU can compute regular languages. LSTM are a subset of counter language, and the similar work they did pointed out these findings. So linear second order RNN are equivalent to weighted automata. So Ravish in his 18 work showed that weighted automata can be extracted from linear second order RNN. Omlin and Giles in the 96 JACM paper did show that second order RNN using SIGMOID activation function is equivalent to DFA. But the most important part of this work is they show that a DFA with n neurons, there exists a second order RNN with n+1 state neurons. So if we assume a fractal encoding for first order RNN, then to derive the number of neurons to recognize any DFA would be n square plus 2mn plus n cube. So it's much more complex in terms of creating a deterministic version of first order network. My recent work and submission do show that similar using second order RNN and using floating point and in finite time, you can have a DFA with only n+1 state neurons. Other work which we published, which we submitted in 2020, shows that sigmoid third order RNN with sigmoid augmented with differentiable stack is equivalent to DFA with n+1 floating point state neurons. So all these work in higher order networks. You increase the complexity, but you can derive what would be the number of neurons you will require to get minimal representation. So it just not shows the equivalence, but it also shows the recognizable capability of these networks. So let's look at some Turing complete model. So majority of Turing complete construction assume rational weights. And if we go with Sabinger's approximation theorem, it's related to real numbers. And it's important to discuss the complexity of this and why it is difficult to get computational model from such construction. So if you wish to devise empirical model, it's important to understand the theoretical limitation and why we'll have a difficulty to create a solution in polynomial time. So let's look at some of the theory in beginner arithmetic. So real numbers can store infinite precision information. So let's consider a simple example. Let's pick a random number between 0 to 1. Since our weights are quantized between 0 to 1, let's assume that as an example. So the number you'll select with probability 1 will contain an encoding of all books, and at least I would say in US Library of Congress, if you assume it exists, they have like all the books out there, or in some cases, World Library. So this is the complexity you'll have when you're dealing with a real number. So rational numbers, you can minimize the restriction using arbitrary precision information using rational numbers. But even with arbitrary precision, rational numbers have capacity to represent any arbitrary precision float numbers and can go beyond that. And the hierarchy between rational numbers and floating point number is infinite. So it creates another obstacle for creating empirical model. Similarly, there is infinitely many complexity hierarchy between real valued numbers and rational valued numbers. So this is where the limitations are with respect to creating a computation model. So let's look at Hava's work, Hava and Sontag's work in 94 and the recent extension in NIPS 21. So what Hava showed in 94 that using infinite precision and time, RN can encode state of a state machine, and using fractional encoding, you can encode state of two stack, which are equivalent to, which can operate as similar to tape. So jointly, this construction using fractional encoding is equivalent to some form of Turing machine. So in the 94 work, what she pointed out is there exists an RNN when 1058 neuron or with unbounded precision that is Turing complete. So one step of Turing machine would require TS to 4. In other words, there is no limit for the computational time. So if you imagine a system, so until you find a solution, the system will keep on running until it reaches the halt condition. So this is not a practical assumption. So recursively computing updates until your model reaches some halt condition. So it's unbounded time in that as well. Finally, compressing memory into real numbers is highly impractical approach based on me, and we cannot design a trainable system because, as we have seen, it has many obstacles in terms of precision, and to create a polynomial solution would take a huge amount of time because all these problems would fall under NP-hard. Second, in NeoRIPS 21, Cheng, who comes from Hava's group, extended the proof, and they showed that with a similar construction, you can get a Turing complete model with two discrete stacks using rational weights. But in this case, the time is unbounded. So it will take at least 3 steps to recognize one step of Turing machine. So the similar thing in Hava's proof, it required 4 steps. In this proof, it requires 3 steps. But still, designing this computational model is challenging because it involves 2 discrete stacks with a growing memory mechanism. So there's no differentiable version with respect to this. And there is no stability argument that the solution constructed by this model would always be stable. Next, I think this talk was also broadcasted a couple of weeks back in the similar group where Pacquiao's in the ICLR and GMLR publication showed that transformers are Turing complete. Since transformers are widely popular in AI community, so this was a significant milestone in proving their limit. But it also have certain limitations. So construction do assume that the inputs that you encode entire input string as opposed to transition table. and is adopted by a fractional encoding work by Howard Sigmund using rational weights. Positional encoding is restricted and cannot work beyond input sequence length. So if we assume positional encoding of n, which corresponds to a Turing machine of the symbol m, then it won't go beyond that. If you have another Turing machine, or if you have if you're categorizing a bigger length symbol, then the construction won't hold true. You have to assume everything to be infinite for this to work stably. Construction also requires hard attention, which is another difficult aspects in making these model stable. Soft attention, even with infinite precision, cannot recognize context-free languages. So Han back in his Tackle 19 publication did pointed these out. I think there is some chart. So Will, can you?
Oh yeah, sorry, I missed that. Gail said, is Pakra's Perez, or am I missing something?
Yeah, it's the
Yeah.
same.
Yeah. Okay.
Yeah, so sorry for that.
Yeah.
Yeah. Finally, it's difficult to show minimal number of neurons required to show above construction. That what is the minimum number of neurons you will require in a neural network to show Turing completeness. So this is the limitation of all the prior work, that you cannot provide the minimal number of neurons to have this construction. So now the question arises that, is this another type of Turing complete model, and why would one care? So we show in our work that our model is not only Turing complete, but it is also Turing equivalent. Given prior work assume rational weights with arbitrary precision and bounded time, we want to show this construction using floating point and finite time. We show a differentiable version of our stack, which is stable. So a 2-stack version is equivalent to a tape, and we show that the tape of this of our model is also stable. So when I talk about stability, it means if you construct a solution by our network, it will always converge within the bound. So if you reach that fixed point, the model will always be true to the ideal Turing machine. So it will always converge, it will always generalize to longer strings. And this is an important property for your system when you're training this using backprop, that all units are differentiable and they are stable within a certain range. Furthermore, what we show is the model which we have constructed, known as neural network Turing machine, will only require n+1 state neurons and m-tape symbols to show equivalence with the Turing machine. Additionally, I'll show that we also show that our network by induction is equivalent to universal Turing machine. Another advantage which we have is in terms of tensor weights, because tensor weights have several computational advantage. So it requires less neurons to train, and it generalizes to Hansen distribution. So Lee, back in his days, published several works to show advantages of tensor networks. And with respect to third order, I have published several works which shows the limit of and the importance of tensor networks.
I have a
One
question.
unique sorry.
So what are N and M here?
So n is the number of state of a Turing machine, and m
Okay.
is the tape symbol.
Okay, cool. Makes sense.
Yeah. One additional importance, or I would say advantages of tensor network is you can insert production rule into the weights of these networks, and you can refine them. So Lee did this in his 89 and 90 NIPS publication, where he inserted rules into the network and showed how they converge. And similarly, I have shown in my IEEE transaction work that tensor network has advantages. And if you train them correctly, they can even beat the modern day neural networks, including stack augmented network and table augmented networks, such as neural Turing machine and DNC, with wide variety of, I would say, error. So let's visualize how third order tensor network would look like. So as I pointed out, it has higher dimensional weights. So as you can see, I think there is some question again.
Yeah, another question came up. So Gail's asking, how many time steps in your model per step? How many time steps in this model per step in the simulated Turing machine?
So it is a one-to-one equivalent. So the step required by Turing machine is equivalent to the step required by our model.
Gail says cool. Yeah, that is cool.
Okay.
Okay.
So as you can see, this is a SIGMOID activation function. You can use any tanh. The weight are four-dimensional indices using IJKL, where you can insert the prior hidden state, input, and stack encoding to compute the next hidden state. So we show that third order RNNs are equivalent to pushed-on automata with stack and Turing machine with tape with finite precision and time. So this diagram would make it much more, I would say, concrete. So on the left-hand side, I show an update for an RNN, and the right-hand side, I show a state transition for PDA or Turing machine. So given we have third order weights, so in your PDA, you have input, the transition, and then there is a stack symbol. So if we add external memory to state machine, we can improve the performance, and we can show that there is one-to-one association with respect to the hidden layer of an RNN, third order RNN, and Turing machine. But this you can visualize if you binarize the weights. But we are more interested into showing that there exists a differentiable version of this, where you can get a solution within finite domain. So this is the heart of a paper where we propose this differentiable activation function, which is a sigmoid, but we show the bound of this. So Will and Gale, they assume saturated function. Turing machine assumption uses logistic function. But what we do here, we show you can design activation function where the solution within a bound will always be stable. In other words, the weight of a model NNPD and NNTM is close to ideal Turing machine based on the sensitivity parameter. So as you can see, let's assume there is a state vector z bar with components between 0 to 1. Then the tensor would satisfy this will answer your question, Gail. So imagine z is your state of TM and z bar is the state of your neural network. Then within a bound, assuming you take h sufficiently larger, they will be ideally close to each other. So this is the construction where in sigmoid you can assume for the sensitivity parameter that the model would always converge to 0 or 1 depending on your epsilon. So in this work, we do point out you have to take S sufficiently larger, and the reader may notice or find it vague that what this sufficiently larger means. So if you take the maximum of all lower bound for H required in all our construction or our proof, you will arrive at a value of H which satisfy all these requirements simultaneously. So this is what one can get. You can determine the lower bound of these models, and we do show the construction with respect to this as well. Next, I also show in my recent submission that the construction which we showed earlier is also equivalent to fixed point analysis or fixed point theorem. So this is Brouwer's fixed point theorem that comes from 1914, which was formalized by Botby in 1971, which shows for any continuous mapping function, there exists at least one fixed point. And in this work, we show that there exists two fixed point. So your model, if you imagine there exists a fixed point, which is close to 0, 0, or 1, your solution would always stay stable. Similar construction was also published by Omlin and Giles back in the JACM work. So when I talk about differentiable stack, what ideally I want is the differentiable version of my stack is equivalent to ideal stack. So we change the stack definition. So there is like different weight matrices corresponding to push, pop, and no op. And ideally, we show that it is equivalent to the ideal stack. So if you imagine discrete stack, my version would require same amount of step, and it will be equivalent to the parametric stack which we propose.
Wait, sorry, can we go back to the fixed point thing for a second?
Yeah.
So if I understand like the fixed point theorem correctly, it talks about when you have a function that you're kind of like recursively applying to an input, and you take kind of like, the limit of the number of recursive applications. What is the analogy of that here? Are you thinking about like an RNN, the RNN gate function as being the function in the fixed point? Or yeah, I don't know. Maybe I just don't follow this part.
So this is with respect to means if you apply fixed point theorem to a sigmoid, right? And if you apply a gate of an RNN to this, you can recursively come to a solution where your model would be close to 0 or 1. So yeah, your assumption is right, but it's showing with respect to sigmoid and the AUTOMATA with respect to a gate. Does it answer your question?
I think so. I guess so. The reason why you can apply the fixed point theorem is because all of the input is represented in every step. So it's really just the same function iterated. Is that right? Like it's not an unrolled ARN. Okay. Yeah. Cool. Thanks.
Yeah, so this is another construction, right? And this you can construct this network using if you calculate the full Jacobian using RTRL. So this is some other work where we show using Jacobian you can get a finite solution. So this is the definition of differentiable stack, and we'll be talking much more about this in the coming slides, where we design a differentiable stack for which has scalar push and pop operation, right? The significance of this particular work is and stack RNN and various version of stack augmented network, you assume everything to be scalar, but there is no finite bound that if the solution would always be close to ideal thing. So we create an ideal representation of a stack, which has different weights for push and pop, and then we show that the differentiable version will always stay stable. So as you can see, for scalar push and pop, we define the stack operators as follows. So remember, H is a sigmoid activation function where capital H is your sensitivity parameter, and K is a vector valued sequence. So it jointly determines the weighted summation of your push and pop, if it is 0, if it is 1. So the differentiable stack operator would approximate push, pop, and no op. So the operator is determined by a symbol pi, which 0, 1, and the vector C would represent the approximate pop operator. Identity is 0, 0, and vector C. And the push operator is 1, 0, C. So if it is close to 0, it's push, it's pop, and if it is close to 1, it's push. The proposition we show is that the differentiable stack is equivalent to the discrete stack. So so it will take exact same amount of step to represent what ideal stack would do when you are working with a Turing machine. So it has one-to-one inclination with respect to this. So a complete working of, I would say, an NPDA in this case, if it is augmented with one stack, is represented as follows. So this is a pictorial view. Imagine an NPDA takes the t+1 input character from your state machine, right? As well as the state represented by Q of t, and a reading RT at the top of the stack determined by the vector KT, which I've discussed earlier in our slides. So by applying weights, WQ, WC, WP plus, which is for push, and WP minus a negative is for pop. So as you can see, there are different set of weights. It's not the traditional neural network which we see. It has slight modification because the differentiability of a stack is important. So it computes and outputs the new state represented by Q of t plus 1, as well as the parameter for the stack action, which is represented using C of t plus 1, push at t plus 1 and pop at t plus 1. The stack is then updated by the operator pi, passing the vector at t plus 1 push and pop operation. So this completes one cycle. This completes one cycle. So this is equivalent to what you see in any PDA or Turing machine. I'll show another construction, just like an example that how the state transition and controls and transition of a network would work with respect to PDA. Let's consider a parenthesis grammar and a PDA with n equal to 2 states. So accept is represented using a simple one hot, one of 0, reject is 0 of 1. The left parenthesis is represented 1 0 0. Then we represent right 0 1 0, and as E would represent your end of symbol. And then there is stack reading where non-empty is represented 1 comma 0, empty is 0 comma 1. So let's look at changes in weights of our controller, right? So if you encounter left, you should not change the state. Thus, the third order weights or the fourth order, if you imagine, you can see the Q is the state of an NPDA, which is also the state of your PDA, right? And this is just 2 states. So an NPDA also has 2 states, where you can see this is how the state transition would be represented when you encounter left. If you have R, then you have to change, then we should not change, I would say, the state unless you analyze your stack reading and if your stack is empty. So in that case, we should change from accept to reject in this following fashion. Then finally, when you encounter end of your symbol, so this construction will work for any string length, even if you pass the billion string length, since it is acting similar to your PDA, it won't have restriction with respect to the string length. And when you encounter end symbol, then it should not change the state until and unless your stack is empty. Finally, changes in weight of your stack. So just for simplicity, I'm showing 0 or 1, but it can be anything between the fixed point which we pointed out. So the only case where you push is when you encounter L, where when you have right, you pop from the element. So this is the weight, the WP plus is the weight for your push, and negative is for your pop. So it does not matter. So it's similar to your no op, right? Whenever you have end of your symbol. So for simplicity, we'll just represent the 2 state, the 2 weight matrices equal to 0. And finally, if there is only 1 character in the stack's alphabet, we set it to be equivalent to 1. So this is the way the entire working of an NPDA works. So the construction we show is the tensor network, which we proposed with differentiable activation function can be represented using following theorem is if you have any, for any given push down automata, right, with n states and m stack symbols, there exists a differentiable NNPDA, NSPDA with only n plus 1 bounded precision neuron that can simulate any PDA in real time. So this is the construction we have because there is equivalence between the simulation step performed by your PDA for simulation steps performed by your neural network, and using the SIGMOID activation function and the construction which we showed earlier, you can show that the solution would converge in finite time and its bounded precision. And more importantly, it will take floating point. Next, let's look at neural network Turing machine. So a differentiable tape can be represented as a paradifferentiable stack. So Hawa in her 94 work and recently Nip's work as well, she represented Turing machine using 2 stacks. So we take this similar approach, and Hopcroft also pointed out 2 stack Turing machine is equivalent to Turing machine with tape, where left stack is simulating left tape, and right is simulating your right tape. So a differentiable tape is a para-differentiable stack K of L, which is defined using the differentiable stack operator, which I've shown earlier. So the stack K is called the right stack, and the stack L is called as left stack. The head of tape would be read using symbol K of 0, and the top of the stack is read using K. So this is the differentiable tape operator, where we define different weights for each side of your stack, where scalar push pop, the similar construction arise, where you show that how these symbols can be approximated by your stack. And in our work, we show that how you combine this to make an ideal tape where the precision would always be finite, and the solution of this tape would always be consistent to the ideal tape which you see, or the ideal two-stack machine. So formally, you can say that the NNTA, right, at any time t, the full state of neural network Turing machine is represented using a triplet. So state, left stack, right stack, where your state is between 0 to 1, which is a vector encoding for your state kt, and your right stack and left stack are representing the differentiable tape operator. So the next pair, where you're calculating the next state, next push symbol, and next pop symbol, can be represented using a dynamic relationship as follows, right? So Q of t plus 1 at I, H is your SIGMOID activation function, weight of your neural network Turing machine, augmented with the previous hidden state, and then minus half is just for sigmoid, is equivalent to a Q of t1, t plus 1. So you can see there's one-to-one association. So this network can unroll backward in time. Next, you show that this your stack pairs for left and right stack. So there is an operator omega at ta plus 1. It can be approximated using the differentiable stack operator, which we have shown. So this is the main theorem where we show the Turing completeness of a model is that for any arbitrary time-indexed sequence encoding of a character string, so it can be of any length, because we are more, since we are equivalent to PDA, so it won't matter what is your sequence length. So if we considered Q, K, and T to be an idealized state and tape sequence. So as you can see, Q bar T, K bar T, L bar T is an idealized state and tape sequence, which is extracted from a Turing machine. And Qt, K to the power T, L to the power T is the sequence of your state and left and right stack of your neural network. Then within a certain bound, if you take H to be sufficiently larger, then you will get that the state of an NTM is equivalent to state of your Turing machine. The state of your left right stack is equivalent to the state of your right stack in your tape. Then state of your differentiable stack left stack is equivalent to the ideal stack which you get from the tape. So you can rewrite the same theorem in terms of stability. So for any given Turing machine M with N states and M tape symbol, there exists a differentiable NNTM with bounded precision neurons that can accurately represent M for arbitrarily long input string. Moreover, we do point out that what would be the amount of recurrent weights and state neurons, the stack size for PDA and NNTM you would require to find a stable solution. So this points out that the bounded precision NNTM is equivalent to your Turing machine, to any Turing machine, and the solution is stable. The computational model which we have designed, if we compare that with stack RNN, NNPDA from Lee, NSPDA was my work, Neural Stack from DeepMind, NTM DNC from Alex Grave, all are unstable when you're using them using gradient descent and backprop. So stack RNN what Mikolov did to work this for majority of on longer strings, he made them discrete. So he approximated certain operations. So there are various tricks highlighted in his work where he pointed out how to train them, how to generalize this to longer strings if you're training this using backprop. To train this networks efficiently, he used a different learning approach which works for the discrete activation functions. But moreover, all the prior memory augmented network uh, are not stable. And in our work, we also show that NNPDA after for longer duration or for longer strings, the stack would behave weirdly. Instead of push, it will do pop, and instead of being empty, it will have some garbage symbols, and the solution of your network will be unstable. This is important. Stability is an important concept because if you are extracting automata from these networks, it's important to show that the network is stable. You don't want to extract some incorrect state representation from this model, or else the equivalence between the two automata would be undecidable if you have like more states. Finally, what we show is the NNTM with only n equal to 6 states and m equal to 4 tape symbols can stably simulate any Turing machine if we assume to have unbounded precision time. So if we restrict, if we remove the restriction and make them unbounded in terms of time, then we show that our model is equivalent to universal Turing machine and can approximate any Turing machine. So this is with the extension of the work from 2007, where the author proposed 4 different universal Turing machine which can approximate any Turing machine. And by induction, we show that NNTM is also equivalent to this and can simulate any Turing machine if we remove the bounded time restriction.
Question about this.
Yes.
The the quadratic time is per step, right? Or is this?
Yeah.
Yeah. Okay. Cool. Thanks.
Yeah. So yeah, so if we add another state neuron for output, you can imagine that only 7 neurons would be important to approximate any Turing machine. So this work is mainly towards approximating things, showing that there exists one-to-one correspondence between tensor networks and Turing machine. The solution constructed by them using differentiable activations is stable, and that is an important property if we are trying to extract state machine. I mean, so you can use L star because in L star you assume RNN to be an oracle. So this machine is acting as an oracle. So that we can use that. You can also quantize the states because there is one-to-one correspondence between the state of TM, PDA, and our network. So it has different advantages, but this is the main theorem which we showed in this work. Yeah, now I'll be happy to take any questions.
Awesome. Thanks. I guess I have one general question. So it seems to me that like stability is a very like useful property. Both it's like theoretically satisfying because it shows this very tight equivalence, but also if you want to think about doing extraction or some kind of like, yeah, algorithmic conversion, it seems like this is a useful property to have. But could you give us a little bit of an intuition about how these stability results proceed? Like when you prove that your version of the stack is stable versus the older stacks are not stable, like what is kind of the key difference there, and how does that work?
So the operator which I created earlier, right? So it has a slightly different definition compared to the stack which we see, right? So you have a stack, right? And then you push pop, and then there is a discrete operator. Now imagine you have a different copies where each weight is corresponding to push, pop, right? So your different set. So to increases the memory complexity, but if you take the summation of these two, it will be equivalent to an idle stack. So imagine this is a push. So I have a weight corresponding to this. I create a vectorized representation of this. then there's a pop, right? So I change these two, I would say, superficial vectors in dimension, and I ensure that the Hadamard product between these two is always between 0 to 1. So that's the difference I have in this work compared to other. In others, you just assume a single stack, push pop, remove those elements from the tape or stack, right? But in this, we assume that different copies, and like each weight, like each operator would correspond that which symbol should go, like which vector should go down, which vector should go up. So in the paper, I do also show that how this parameterized version works by in graph, that how these weights are getting pushed and how these weights are getting popped out. And ultimately, you want everything to be 1. So you will see that these vector representation converges to a stable solution. But discretizing everything does not work stably with backprop. That's what I have seen. And I have implemented, like I have published few works in stack RNN, where if you want to discretize the stack operator to make them stable, then I had to use unbiased online recurrent learning, which is like the approximation of RTRL, to get full Jacobian, and then that model is slightly stable compared to the model which are trained using backprop, because the differentiability is like an important property, and the stability, that's the reason stability is a key approach in this stage.
Would it be possible if you wanted to train the discrete stack with backprop to use a straight through estimator? In other words, on the forward pass, you use the discrete value and then use the gradient associated with the approximation.
Yeah, I did try that, but the states of the controller does not converge.
Okay.
So what I've seen, the states correspond to something random. I did try using state through estimator, where when you use the skip connection through your gradients, the states are unstable. So if you check the RNN or the LSTM, so I had RNN plus LSTM augmented with this type. So the state of these network were unstable, because since you don't have one-to-one correspondence between the transition table and the state of your of your PDA and the state of your state machine extracted from your neural network, network behaves weirdly. It does not converge. So I tried the state to estimator with high order network, and since you can insert, so the ITable transaction paper, which I highlighted earlier, right? So I can insert the rules, like the transition table, into the weights of my RNN. And I do show if I do this guided kind of approach, and if I use the discretized version, because in that I use discrete stack. So I use state estimator and reinforce unit. And I showed that using only 8 neurons, my model can learn stably on longer sequences. On the other hand, NNTM, DNC, they failed. Like as you increase the string length, the performance starts deteriorating. And that's where I talk about stability, that beyond your distribution, you should still converge, because automata can converge to unseen distribution easily.
So Gail has another question in the chat. She's asking, which language did you learn with 8 neurons, and how many have you found you need in general for different tasks?
So I use palindrome, then Dyke languages, parentheses. So then A raised to N, B raised to N, C raised to N, D raised to N plus M, these toy grammars. But yeah, there was a Dyke grammar, because parentheses come from Dyke 6. So I did try on Dyke grammar. And the solution of my model is always stable. So, and other question she had was with respect to different tasks.
Yep.
So how many?
I guess like how does the complexity vary across different tasks? Like how many neurons do you need?
So the maximum number of neurons I required was for Dyke, where you had 4 characters, but that was close to 12, and minimal number of neurons are required was 7. So it's always empirically, it's always n plus 5. That's the maximum thing you will require. So if the state of the number of states in PDA is, let's say, 100, then I'll require close to 105, 105 to converge better, assuming I insert some prior rules into the network. But yeah, it would be always n plus 5.
But in theory, it could be less than that, right?
In theory, it's n plus 1, yeah.
Yeah.
But I show using RTRL. RTRL is expensive because it's n raised to 4 in terms of time complexity and memory, right? But if I take the full Jacobian, then I converge in n plus 1. So in n plus 1, I can find a solution. But that's using RTRL. If I use backprop, I need to add different tricks and some additional computation to make these models stable. Have you played around with any NLP task? Not yet. One approximation I had, which I published in Triple AI, where I approximated the second order weights and added a differentiable, a different version of differentiable stack into the memory. There, I did show for mathematical reasoning that the higher order networks do work well compared to vanilla networks, but not towards the NLP task. Means like language modeling, language recognition. I haven't done that. That's something which my current student is working on, like for creating a probabilistic graph based on these things. But yeah, means these papers should be out in a year because we already have results, but they will be out in within a year, depending on reviewers give us review in time. Yeah.
Hi, I have a question.
Yeah.
Hi, Ankur. So thanks for the talk. So I was curious about the role of the sensitivity parameter in the activation function.
Mhm.
So it looks like this version of the stack is based on the stack of Julien and Mikolov 2015, with a difference being where the activation function is placed in the stack. So I think in the old version, it's just applied to the vector that's pushed at each time step to the top of the stack. Whereas in this version, it's applied to all the elements at every level of the stack at each time step. So I was curious, it seems like the sensitivity parameter is necessary to ensure that the model converges.
Yeah.
So like if you were implementing this and you wanted to train this model with backprop, what would be a practical way to choose the sensitivity parameter to ensure that you can reach a solution that converges?
So to get this, the one work which we are trying to do is we run different simulations, right? To determine the sensitivity parameter. So you can run the simulation and see what is the average way your model is converging towards, and then you can decide that sensitivity parameter based on this and encode that into SIGMOID. And if you
Okay,
train the network after that, the network would be stable.
gotcha. So you just treat it like another hyperparameter.
Yeah.
You could probably train it with backprop too, right?
Yeah, I can train this using backprop. Means in my older work with these networks, I train this using wide variety of learning approaches. So it's
Right.
backprop, Euro, RTRL. I have my own learning approach, so I've used that as well. It was just to show that you can train these networks. All network has their own all learning approaches that have their own advantages, right? But still you can stably you can train this using backprop. It's not a big deal. The only thing is avoiding the vanishing gradient, because the credit assignment issue would become worse in tensor networks if you don't if you like randomly pass out certain hyperparameter. So imagine a 4-dimensional weights, and then your gradient descent is you're backpropagating through entire thing, right? So your gradients are going to get vanished at certain points. So there is a various stabilizing scheme which I have shown that how you can stabilize them to ensure that your gradients don't vanish. But yeah, if you take care of these things, your solution would converge.
Okay, so there's a solution that exists that's stable, but reaching
Yeah.
it with gradient descent might be challenging.
Yeah.
Okay. Yeah, it's always a difficult problem with these recurrent nets. So
Yeah, that's true. Like with recurrent networks, there is so yeah, another work which we are doing is creating a stabilized learning approach, which is local. So that would be out in like 6 months. But yeah.
yeah, look forward to it.
Okay.
Cool. Well, I think we're a little bit past the hour. So
Mhm.
if there's one or two, if there's another final question, we can take that. Otherwise, I think we can thank Ankur. Okay, so yeah, thank you for the talk. This was great. I think I'm gonna look more into all the stability stuff now, and yeah. And you're okay with uploading the recording, right?
Yeah.
Great. All right.
Thank you, everyone. And if you have any queries or if you have anything, let me know. And it was great seeing Automata people in this group. Yeah. Thank you.